Anyhow, we means maybe we can wait for some time because BTech will join soon.
गुड मॉर्निंग सर।
Good morning.
सर वन रिक्वेस्ट सर।
Yes.
सर वो आपने स्लाइड शेयर नहीं की सर, हम क्या घर पे रिवाइज करना होता है, कर नहीं पाते, मटेरियल भी
सॉरी मैं आज कर दूंगा। मैंने कल अपने लेक्चर और सारे वो डाउनलोड कर रहे हैं। होपफुली
ओके
मैं
सर।
आज सबसे पहले वही करूंगा। ठीक है।
ओके सर, थैंक यू सर।
हम्म। Okay, I think now we can slowly start because it's 8:30. I have given the deadline for BTech students that only. They have actually some breakfast issue in the morning, so they just requested to delay it for a 15-20 minutes. But anyhow, we can start it. Okay. So today we are interested to discuss about the retiming. Now, it's here. So we are interested to discuss about the retiming. So this is your chapter 4 of KK Party. Okay. Even retiming concept is available in a miscellany. Probably you have gone through for your synthesis CAD VLSI. Okay, over there in a miscellany book also for a sequential level optimization. This concept is there. Okay. Now, specifically, I want to start with a chapter 4 and then maybe we would like to go to chapter 2 and 3. The reason is that this is somewhat very important that you should understand first before starting any kind of optimization. Anyhow, this is also one of the optimization. So now onwards, what we will see in our syllabus that we will discuss about the different types of the optimization. Now, optimization could be at the architecture level, maybe at the gate level, maybe at the transistor level. Okay. But to just align with the subject, we will stick the optimization at the architecture level because we will talk about always architecture at our VLSI SPA subject. Okay. So at the architecture level optimization, if I want to optimize a speed, okay, that means I want to improve the performance. So at that time, retiming is one of the concept which you can use it. Okay. Now, what retiming do and how the retiming would help you. So that we will mainly discuss. Okay. So whenever we want to go for a optimization at the architecture level, then we will talk about always graph. Okay. So we will first design our circuit in terms of the graph and we will apply the optimization approach on this particular graph. Now, when I talk about the graph, then graph of can be of different type where some sort of node like this and you have some edges which are being connected with the node. Now, this node is my functional unit and these edges will define the relation. So node, when I consider in a graph, then you need to consider that those are the functional unit. Now those functional unit could be anything, adder, multiplier, your Poldic block, anything. Any functional unit could be represented by your node. And how these functional unit are being connected. So that means how the data is flowing from one node to another node. So that is nothing but the connection between the block. Okay. So that is being represented by these edges. Okay. Now this suggests that this functional unit, let's say that I am denoting the name of the node. So node 1. So node 1 is a one functional unit when it will execute the function and then it will pass the data to node 2. Again, node 2 will take the data from node 1. It will process on that data and then it will pass the data to node 3. So this way you need to understand that how the data is flowing. Okay, so that's why it is a data flow graph representation. Now, when I say the data is moving from node 1 to node 2, so whatever the edge is there, for the edge, there is another representation that we used to have is a weight. Okay, so always the edges are being represented by a weight. So weight is just to define a delay, and that delay you need to understand it in terms of the clock. Okay, so this delay could be of this will be always in terms of the D, and this could be D, 2D, 3D, like that. So what this conveyed at 1D, that you need to understand is a one clock delay. 2D, that means 2 clock delay. Similar way, you need to understand 3D, 4D, 5D. So you can have a delay for a particular age of any order. Okay. Now, for this data flow graph, once you able to get this information from your circuit, okay, so any architecture is given to you or any block level representation is given to you for any DSP application, then ultimately you need to draw the DFG graph, where in a DFG graph you need to first identify that what are the nodes which is you need to map as a functional unit of your architecture, and connection between the functional unit you need to understand with the edges, and this edges is having some sort of finite weight. Now if there is no weight is being defined, then you need to consider that W is 0D. So this weight could be starting from 0, it could be any integer, and if for a particular age there is no weight which is being defined explicitly, then you need to consider that weight is 0. Okay, so this is all about the basic concept that you need to understand. Okay, now I am just quickly going through a PPT also parallelly, and then we will come back to this. Okay, now what is the need of the retiming? Okay, so large delay of a particular block decide the clock frequency. So what is the meaning of that? That for any particular system, okay, maybe you have a, let's say that 10 number of blocks. Okay, each and individual block would take some time to execute. Okay, so maybe you have block 1, block 2, block 3, block 4. All are a different block which represent a different functionality, and for a OR block, so block is nothing but your functional unit. Okay, so that functional unit is having some sort of delay. Okay, so those delay of maybe of any integer value. Okay, so let's say that functional block is having a delay 4, functional block 2 is having a delay 5, functional block 3 is having a delay 6, and all the remaining functional block is having a delay 1. Okay, so what I want to say that key for this functional block, when I say this functional block, then this functional block is also having a delay. So when I write down in round bracket some value, then that represents the delay of this functional block. Okay, similarly every functional block is having some delay. Okay, you will not find out any functional block there where there is a no delay. Ultimately this functional block is nothing but our hardware, and we know that any hardware we consider, then there would be some delay. Okay, if hardware is there, then at least it will take 1 clock cycle to execute the performance. Okay, now when you have a n number of functional blocks and they are being operated in a one particular clock. Okay, now this functional block 1, functional block 2, functional block 3 having some delay. Now I am defining the delay. Let's say that here it is 4, here it is 5, here it is 3. Now I need to provide the clock to this particular system. Now this, consider that this is a 4-unit delay, or just for a better understanding, define that it is a nanosecond. Okay, so this is a delay of functional block. So that means this particular block requires this much time of your clock. So now when I want to define a clock period of this particular system, see clock is common. Okay, so now I need to take care of the consideration of all 3 blocks. And if I look at this particular functional block 2, which require maximum number of time, how much time it require? 5 minutes. So that means if I want to apply the clock for this particular system, then I need to ensure that it should have a time at least 5 nanoseconds. If I provide lesser than that, then this system may not work properly. Of course, this will work for a 4 nanosecond. This will work for a 3 nanosecond. But when I say a common clock to all the block, then I need to always think about a block which will take maximum number of time. And according to that, I need to decide my time period. So this time period, when I say t is equal to 5 nanosecond, so this ultimately tells me what will be the operating frequency of this particular system. Time period is nothing but inverse of my frequency. So frequency could be easily identified once you know this particular t. Okay.
तो हाफ टाइम पीरियड के लिए ना सिर्फ 5 मिनट ऑन टाइम या ऑफ टाइम
नहीं, okay.
इनपुट चेंज हो जाएगा सब.
Okay. So whenever we decide a clock, so clock will always have a duty cycle 50%. That means t on equal to t off. Okay. When we talk about the pulse, then pulse may be having a t on and t off differently. But when I say a clock, then a clock will always have t on and t off. So that means the duty cycle is 50% only. So over there is no difference of a t on period and t off period, and that is the property of the clock. Okay. When I say pulse, then for the pulse it can be a general thing where you can have a different duty cycle for a t on and t off period. Okay. But for a clock, always it is a 50% duty cycle. Okay. So that means the t on period is 2.5 and t off period is 2.5. If I consider the total clock period is 5 nanoseconds. Okay. Now the point which was I am talking about, that once I think about the system, then always I need to think about my worst case block, because my total system performance is depending upon my worst case block. Okay. Because of this block, I need to now consider the minimum period for this particular system is 5 nanosecond. As it is a 5 nanosecond, so depending upon that, the frequency of this particular system is being decided. Now, retiming is basically a concept where I want to optimize my speed. So I want to optimize my speed. So that means I want to increase the frequency. So that means my f should be increased. If I want to increase my f, so what it will say that my t should decrease. So maximum operating frequency should increase. So in other way, my time period should decrease. Okay. Now, how I can improve the performance of this particular system? There is no way that to think anything else. We need to concentrate about this block, because this block is a culprit, and because of this block I have decided on my clock frequency. So in a system, always you need to think about the block which is taking a maximum number of time, and once you try to reduce a time execution of that particular functional block, then you could improve the overall performance of the system. So over here, if I want to increase the frequency of this overall system, then I need to decrease the time. Now, how the time is being decided? Time is being decided by this functional unit 2. Why? Because this is taking a maximum number of time. So ultimately, always I need to think about. So when I talk about the graph, in a graph, as I said that this functional unit is nothing but my node. Okay. So in a graph, I need to always worry about that which particular node is taking maximum number of time. Okay. Now in a graph, when I say that you have some delay. Now let's take some specific example that this particular block is having a W delay. Okay. and this particular block is having a no delay. Okay, and this particular block, let's consider that having a 2D. Now what I mean by D? Number of clock. That means once a node 1 will execute, then after a 1 clock, the data will go to the node 2. Now over here, for this particular edge, when I go from 2 to 3, there is no delay. Okay, so what it says that once this particular block executes, that is the time 4, and the 3 should be executed at the same time. That means for a one particular clock period, if I talk about this particular clock period, so for this particular clock period, this both the node which I consider as a functional unit should complete its execution. Am I right? Because there is no delay. So this and this has to be completed in a same clock cycle. Now I am considering the delay of the node 2 is 4. The delay of the node 3 is 3. So what it says that in order to complete this functionality from node 2 to node 3 within one clock cycle, I need to ensure that the period of my system clock should be 7 nanoseconds. I hope you are with me. As there is a no delay. So no delay, that means what it suggests that it has to be executed in a same clock cycle. So that means node 2 will take 4 nanosecond time. Then it will provide the data to node 3. Now node 3 will take 3 nanosecond time. But as there is no delay, so what is the understanding? That it has to be complete within this period. Okay, and that has to be a one clock period because there is no clock delay. So that means there is no clock delay. So I need to add this and this time, and then I need to think about what should be my minimum period of the clock. Now here,
Excuse me, sir.
yes.
Sir, actually, it is hard for us to trace your pointer, sir. We are getting confused on where you are actually pointing and explaining.
Okay. Okay. So maybe I will now put some indicator. Okay. Okay. So I am just pointing out for this node 2. Okay. Now I am using the red line to point out the things. Okay. So I am talking about node 2 and I am talking about node 3 and I am talking about this particular edge. Okay. Now what I am talking about that this particular edge which goes from 2 to 3. Over there is no delay. Now what I mean by that, if there is no delay, that means this execution has to be completed in a same clock cycle. So if I talk about node 2, so node 2 is having a delay of 4, let's say that nanosecond, 4 nanosecond delay, and then it will provide the data to this particular node, node 3. Now it will take 3 nanoseconds. So 4 plus 3. So that means 7 nanosecond time I require so that this 2 and node 3 both could complete the time or complete their execution. And in a same clock cycle because there is no weight which is being assigned to this particular edge. So according to that, if I think about considering this particular system over there, for this particular system, I need to think about that 4 plus 3. 7 nanosecond is the minimum period that I need to provide to my clock so that this particular system could work easily. Now, there is a one edge from 3 to 1. That is also there. So here, what this connection says that I am talking about this edge. Okay. So this 3 node will take 3 nanosecond time. Then after a delay of 2 clock, it will provide the
data to node 1. So here there is no restriction because there is a difference of the clock. If there is a difference of the clock, then we do not have to worry about. If something we need to complete within the same clock cycle, then we need to worry about, because that actually reflected in a minimum period which we require for our clock cycle. Okay, so here when in an age you have a delay, then ultimately we are talking about an operation which happens at the another end of the age at the different clock period, not the same clock period. Okay, so that means for this particular clock, if I am talking about, then this particular operation, not necessary that it should be completed in this clock. It should be completed after some another clock, and that is being defined that after a 2 clock period. So here we do not have to worry about it. Similarly, for node 1 to node 3, if I am talking about, then for the node 1 to node 3, again we have a delay of 1 clock. So that means once the node 1 is complete, and I am talking about node 2 execution, then also in between there is a delay of the clock. So that means I am talking about the another clock now, where this node 2 will perform the functionality. Okay, so over there we do not have to worry about. Where we need to worry about mainly where there is an age and there is no delay. Okay, what I am trying to say here for this particular graph, why 2 to 3, this particular age is important, because this is the age where there is no delay. So here there is no wait. So ultimately wait is 0. So what it implies me that this execution of the both the node has to be completed in a same clock cycle. And as I need to complete the execution of these two nodes in a same clock cycle, according to that, I need to think about that what should be my minimum clock period. Now that minimum clock period ultimately decide my, so this is T. So this T will decide my F. Okay. Now for this particular graph, when I say this particular age, then this is basically defined as a critical path. This node to this node along with this age, this is being defined as a critical path. Why critical path? Because for this particular path, whatever the operation I need to perform, that has to be performed in a 1 clock cycle only. Okay. Now, if I want to improve the performance of this particular system, then ultimately I need to reduce this critical path, or rather than to say that whatever the delay, so here this is a critical path, and if I say critical path delay, the critical path delay is a value. Now critical path delay is 7 nanosecond. As critical path delay is 7 nanosecond, I am deciding my minimum clock period as a 7 nanosecond, and the frequency is nothing but 1 by 7 nanosecond for this particular system. Now if I want to improve my frequency, that means increase my frequency, I need to reduce my this critical path value, that is T. Whatever the T value is there, I am talking about. If somehow this value from 7 to I can bring back to 6, 5, 4, 3, then my frequency would be increased. So that means in order to increase the frequency, I need to decrease my time. Now, if I look at this particular block and decreasing the time, one thing is sure that this particular block require 4 nano, this require 3 nano. So one of the way to do that, maybe here this is a critical path because this is a delay free path. Critical path is also termed as a delay free path. Why it is a delay free path? Because there is no D element over here. Here there is a D element, here there is a D element, but at this particular age there is no delay element. So when I say critical path, then critical path is always termed as a delay free path. Okay, so in a reverse way, if I want to find out a critical path in my particular graph, then what I need to do, what I need to look at, I need to look at the part where there is a zero delay, or in other words, there is a delay free path. I need to find it out in my graph. Once I observe the delay free path, then I need to find out what is the delay which is being associated with this particular path. Once I found a one particular value for a delay, then I can think about that what is my frequency. Now, if I want to increase the frequency, then I need to ultimately reduce this part. Now, for that, what I need to do? The best thing that I can do is, there is no delay over here. If in this particular edge, somehow I can manage D, presently there is a 0D. But if I can have a 1D, 2D or any D, that suggests that now the node 2 will take 4 nanosecond time, and then node 3 in another clock require a 3 nanosecond time. So ultimately what I need to do? I need to insert a D somehow over here. So that concept of inserting a delay in my particular graph is basically defined as a retiming. How the time is changed? Because now if I consider that there is a D over here, then this node 2 require 4 unit time, this node 3 require 3 unit time. Now the minimum period of my system got changed. क्यों? क्योंकि पहले मुझे 4 plus 3 within a 1 clock cycle I need to complete. Now I have a delay. So that means this would require 4 nanosecond in a one particular clock period, while this require a 3 nanosecond in another clock period. So now for this particular system, if I consider that there is a D over here, then now for this particular system, I can consider that the minimum period which I can set. What could be the minimum period of this particular system? It should be 4. Very good. Because here it is 2, here it is 4, here it is 3. So now, just I talk about, I need to think about the functional block which takes the maximum delay. So here this will take. So this is 4. If this is 4, then now I'm 1 by 4. So that means my F is increased because I have reduced my time. So timing of my particular graph got changed. So that concept is basically defined as a retiming. Okay. Now objective is clear. Yes.
So if initially there was a delay in that critical path, then which would be our critical path?
If there is a delay over here, okay, still here if there is a delay, then actually the critical part of the circuit is a part which is taken by a or a time which is taken by a one particular functional unit. So here we are considering that this 4 unit. So this 4 unit is a critical path delay for this particular circuit. So when I say consider a node, then node is ultimately one functional unit. So that means ki, let's say the architecture is for a adder. So there is a one adder circuit. So inside the adder, definitely there will be a critical path. And according to that, we have decided that the adder will take 4 nanosecond time. Okay. So if in all edges you have a delay element, then ultimately the critical part of your circuit depends upon the functional unit. Now critical part for that particular circuit is now the maximum delay out of all the functional units. So here the functional unit 1 is taking 2 delay, functional unit 2 is taking 4 unit delay, functional unit 3 is taking 3 unit delay. So out of all these 3, functional unit 2 is taking 4 unit time. So that means my critical path delay is now restricted to 4. As the critical path delay is 4, now my minimum period is 4 and my critical frequency is 1 by, or sorry, my maximum frequency is 1 by 4 nanoseconds. Okay. Now, so what would be the base circuit for me? The base circuit for me that whenever there is an edge, there has to be one delay element. What I did say just now, I say that if there is an edge and if for that particular edge, if I have a delay element, then that would be the base part for me. If there is a delay in between, that means that whatever the other functional unit that has to perform the block or that has to perform the functionality in another clock cycle. Now another thing is for this particular diagram, if I think about getting the base performance is the minimum period that I can achieve. What could be the base performance of my graph? The base performance of the graph is the maximum frequency that I can achieve. The maximum frequency is equal to the minimum period of this particular graph. Now what could be the minimum period? The minimum period could be the maximum delay of a particular node. Okay, again I am rephrasing my word. Okay, so what I mean to say that for this particular circuit or this particular graph, if all the edges have a delay, then that would be the base case for me. Now for that particular time, still the minimum period of my clock is required. That would be decided by a maximum delay of a particular node. All of you are agree with me? Okay. Now the base performance that I can get for this particular graph is this, which is the maximum delay of my graph. क्योंकि अभी इससे कम कर नहीं सकता. अगर मैं if I reduce my time period lesser than 4, then this particular unit may not be able to perform its functionality. It is something like that what I discuss over here. For this particular graph, what would be the base performance? The base performance is the clock period or minimum period is 5 nanoseconds. Because I need to think about this particular block which takes the maximum number of time. So for this particular graph also, the base performance that I can get is the minimum period I can set 4 nanoseconds. I cannot reduce my time for this particular graph lesser than 4 nanoseconds. Otherwise, this particular functionality which is being represented by graph, it is not being performed. I hope you are with me. Okay. Now, the problem is not this much of simple. Okay. So when I say I want D, okay, so initially there was no D over here, but I want D over here. What the actual theorem of a retiming says that I cannot bring the new D inside my loop. I need to somehow manage from the other edges to borrow a D over here. Okay, so what I mean to say that in a retiming concept, when I want to introduce a D at a one particular edge, then I cannot bring the D outside. I need to actually take out the D from any of these particular edges. Okay, so what is I mean to say that the number of delay element in this particular loop should be same. That number of delay element in a particular loop has to be maintained. So that means here the number of delay element is, when I say a loop, 1, 2, 3, 1. So there is a loop. So in this particular loop, the number of delay elements are no. Delay element, that means I am talking about D. This is a time taken by a node. And this delay element says that a clock in terms of the clock. Okay. So number of delay element in this particular loop is 2 plus 1D. Because here I have a 1D, here I have a 0D, here I have a 2D. So that is a 3D. Now whatever I need to do, I need to deal with this 3D value. I cannot introduce another delay element over here if I introduce, then the concept says that the functionality will get changed. So that is a one theorem that also we will see. So the retiming concept is, if I want to put a D over here, then I need to take out the D from any of these edges, so that in a loop the number of delay element is maintained. क्योंकि लूप में टोटल नंबर ऑफ डिले एलिमेंट 3 है, तो अगर मैं अपने परफॉर्मेंस को इंप्रूव करना चाहता हूं तो उससे मैं डिले एलिमेंट की पोजीशन को चेंज कर सकता हूं, लेकिन नंबर ऑफ डिले एलिमेंट की वैल्यू को चेंज नहीं कर सकता. That means total number of delay element is 3. Then if I want to optimize, then also after optimizing also the number of delay element inside the loop is should be 3 only. So how you can do it and why it is that we will discuss. Okay. So just to give you the brief, I think this is enough. Now I am going back to the PPT to just try to understand that what the word meaning is that. Okay. So let's okay. So now I am going back to this particular PPT. Now here what this says that the larger delay of a particular block decide the clock cycle. So larger delay of a particular block decide the clock cycle. I think this you are getting. So what is meant to say that in your particular system, whatever the functional unit which take the maximum number of time, according to that your clock frequency is decided. That's what we just talked. If functional unit take 5 nanosecond, and because of this 5 nanosecond, the system will take minimum period 5 nanosecond. Or if a particular graph I am talking about, then for that particular graph, node 2 is taking time 4 unit. And because of that, for that particular graph, the clock frequency we are considering as a 4 unit. Okay. So the largest delay of a particular block decide the clock frequency. Clock depends on a delay free path. What is the critical path? We have just mentioned. The critical path is a path where there is a no delay. So that means your performance of a system always depends upon your critical path, and that critical path is always a delay free path. Okay. So in a delay free path, all the operation has to be performed in a one clock cycle. Okay. For node 2, node 3, that 4 plus 3, I need to complete in a one clock cycle, and that's why the clock period we have set it is a 7. Critical part is a delay free part of a maximum delay. Okay. Clock cannot be set shorter than critical part, and time required for the same is a critical part time or critical part delay. Okay. So my clock is always equal to your critical part. It cannot be lesser than the critical part. Throughput is depend upon the computational time. So throughput is one of the word that we will try to understand. So usually throughput is a number of output that I am taking with respect to clock. Okay. So that is the term. Probably it is not directly related to the retiming, but when we talk about the pipelining and parallel processing, at that time we will deliberately discuss about what I mean by throughput. So reduce the critical timing will maximize the throughput or maximize the clock frequency consider. So retiming will help to achieve the improvement in clock frequency. So that means if I somehow reduce my critical path, then I can increase my clock frequency. That means my speed is now improved. So what is the retiming? Retiming is a transformation technique used to change the location of a delay element in a circuit without affecting input-output characteristic of the circuit. Now that is very important. The last particular word which we need to understand that without affecting input-output characteristic. Okay. So when I think about optimization of any particular graph which represent a one particular circuit, then I do not want to change the functionality of that particular circuit. I need to ensure that the functionality of my original circuit should remain same. It is something like that if I want to do, let's say, some sort of, let's say that FR filter I want to implement. Okay. Now, if I want to improve the performance, that is improve the speed for my particular system, then after the improvisation of the performance, I would like to achieve the same functionality. It should be, if it is a FIR filter, then it should perform the functionality of the FIR filter only. So this is a golden rule for any optimization, that your original performance, whatever you are getting, your original functionality, rather than performance, I should say that functionality. The functionality of that particular system should not change. So this technique is a synchronous circuit design. Of course, we are talking about the clock, and the same clock is being applied to all the blocks. So when I say in this particular graph, we have a different node, and I am considering that this node which represent the functional block, these all are being governed by a same clock. So that means we are talking about only synchronous design only. So retiming concept is cannot be applied to a asynchronous circuit. Always, if a synchronous circuit where the same clock is being applied to all the blocks, then we can apply a retiming concept. Pipelining is a special case of retiming where throughput is increased by inserting the buffer. Now, pipelining is one of the concept, maybe at this word you have heard at the time of the microprocessor, because microprocessor is basically using a pipelining architecture. Okay, so pipelining is actually one of the special case of retiming. So pipelining is also a retiming, but where there is a allowed, you are allowed to insert a buffer. Just now I have told you that probably in a retiming I need to just change the position of my delay element. The total number of delay element inside the loop should remain same. But when I talk about the pipeline, then there is no loop. So at that time, I am allowed to insert the any new delay element. But when I am talking about the loop, then for a loop, there is no way that I can insert any buffer. If I insert any buffer, then ultimately the functionality would get changed. Okay. Okay, now just to understand the pipelining concept. So for a pipelining concept, oh sorry, for a retiming concept. So for a retiming, there are two methods to do or to apply a retiming concept. Okay, one is a optimization through retiming vectors, and another is a cut set retiming. Now cut set is same concept what you have actually seen on your network theory. Okay, so same concept is applied over here. Another concept is a optimization through retiming vector. Okay, now when I want to optimize through a retiming vector, then what I want to do, I want to set some retime vector value to a particular node. Okay, so that probably I will explain with the example. So I think this we can see. Okay, now when I apply the retiming vector method, then the weight gets changed for that particular age. Okay, so whenever I apply the retiming, then ultimately the weight of that particular age should get changed. Okay, so the new weight after applying the retiming, the new weight will be defined like this. The equation says that WRE, that means the new weight, is equal to WE, which is my old weight, plus RV. RV stands for retiming vector value for my node V, and RU stands for retiming vector for my node U. Now let's try to understand it with the example. Okay, so just I am going back to this.
Maybe I can erase. Yes, save changes. Okay. So now, as I just mentioned that for retiming, two methods are there: retiming vector and cut set retiming. So now try to understand this both the method one by one. So first let's consider the retiming vector. Okay. So just to understand the retiming vector, let's consider one particular node U, another particular node V. Both are being related with each other by this particular edge. So what this suggests that the node U will perform its functionality and the output of node U is given as an input to my node V. And over there, let's consider the weight is basically D. Now there is another edge which goes from V to U. So that means the node V will perform the functionality and after that it will pass the data to node U. So this is a one simple graph which is given to you. Now for this particular graph, I want to improve the performance. Okay, that means I want to apply the retiming concept and with that I will need to increase my speed. Okay, now whenever you want to apply a retiming vector method, then one formula that you need to always understand. So when I apply a retiming concept over here, then consider this weight is a W old. Then there is an equation which just mentioned in the previous slide. W new is equal to W old plus R of V minus R of V. So that means if for this particular graph, if I apply a retiming concept and if I will have a new particular graph U and V, which is a retiming version, this is a retiming graph. For this, the W new is this one. W old, that means before applying the retiming, what was the original weight plus, sorry, okay. Now for this particular graph U2V, there is a original weight W old. Now when I apply a retiming concept, why I want to apply the retiming concept? Just to improve or increase my speed. So for that I will apply the retiming concept and then I will get a new graph which is this one. So over there the W new would be W old, that is my original weight, plus RV minus RE. Now RV is retimed vector of node V and RU is retimed vector of node U. ठीक है. Now this retime vector we need to assume, but there are some rules to assume this value of retiming vector. This we need to assume. You can assume any value, but that value has to be integer. So RV, RU could be any integer value. And you need to ensure that with this RV, RU, whatever the W new that you are getting,
that should be always greater or equal to 0. What is W? W is a weight. W is a weight. Weight will be always defined in terms of the delay element. W is a weight. Weight always defines the delay element. So delay element can be 0. That means there is no delay element. Or there could be one delay element, two delay element. So that means always an integer. Okay. So you need to ensure that this W new should be integer. See, W old is a delay element. There has to be integer value. RB and RU, if you take an integer value, then W new would be integer value. But of course, you need to ensure that this W new, which actually defines the weight of my retime graph, that has to be some realistic value. So realistic value of a W is always 0 or greater than 0. When I say a negative weight value, then there is no negative cycle. Okay. So ultimately, the weight has to be 0 or any positive value. So whenever we are assuming RV and RU, as I said that RV and RU has to be any integer value and they have to ensure that W new should be greater than 0. So this condition you need to satisfy, and with that you need to assume the value of RV and RU. Now let's try to understand the retiming for this particular graph. Okay, I am just rewriting my equation so that you remember W old plus RV minus RU. Now always remember that this is RV minus RU. So that means destination. If for this particular graph I consider this is my source node, this is my destination with this particular edge, because from here the data is being generated, data is being passed to, sorry, what happened? कैसे हो गया? मैंने तो कुछ किया नहीं. 1 minute. Okay. Now I need to again open. Okay. Good. So what was the point I was talking about, that when I write down this equation for a retiming vector, so over there RV is there minus RE. So what this says that destination node retime value minus source node retime value. As the data is being produced as U and the data is being passed to V. So V is my destination node and U is my source node. So always try to understand that W new is equal to W old plus retime value of my source node, retime value of my destination node minus retime value of my source node. Okay. Now think about applying this concept over here, and at the same time just RV and RU should be integer. MTech students, I request if any question then you can ask. If you are writing at a chat box, then I can read at the end only, because I have make it a full screen over here, so I may not be able to read it. So please excuse for that. But if you have any doubt, then please ask. Don't wait.
Excuse me, sir.
Yes.
सर ये U और V इसमें से सोर्स और डेस्टिनेशन कैसे डिसाइड किया?
ये जो एज है वो एज की डायरेक्शन क्या है, कहां से जा रहा है?
यस, समझ गया सर.
Age direction is from U to V. Okay. So U from data which is generated from U, it will go to V. from this particular edge, ये जो एज की डायरेक्शन है ना, इससे मुझे पता चला कि ये डेस्टिनेशन है, ये सोर्स है। ओके, ठीक है। नाउ I need to apply this concept. So let's consider that I am talking about retiming vector concept now. So for this particular graph, let's assume that here the delay is t, here the delay is t. So t is you can consider the delay which is being defined. Okay. Now for this particular graph, if I look at this particular graph, I am interested in a retiming concept. Okay. So retiming concept is always applied to my critical path. So in a graph, first I need to find out the critical path so that I can start my retiming concept. Retiming concept is always, we are interested in a critical path because for that part we need to reduce the delay. Na? We have just discussed before 15-20 minutes back only that for a critical part we need to target, and for the critical part we are interested to reduce the delay. So now in this particular graph we need to find out the critical part. What is the critical part? So critical part for this particular graph is V to U. This is V and this is U. Sorry if my handwriting is bad. Okay, so this is U, this is V. So V to U, that means we are talking about this particular part. Okay. What is the critical part delay? Critical part delay or critical part time, both the terms are same. It is 2t, very good. This require a t time and then it will pass the data to this unit where it requires t time. So that means my critical part time is 2t. Now for this particular graph, if I want to apply a retiming, then what the best I can get? I can get critical path after retiming at most t, not lesser than that, because the t time is anyhow required for a one node execution. इस नोड को जितना टाइम चाहिए, इस नोड को जितना टाइम चाहिए, that I need to provide. There is no way that I can reduce that lesser than t. So ultimately I can go from 2t to 2t. So that is in my mind that best I can get. Now this is possibility. Okay. Now applying a retiming, I need to explore this possibility that whether I can get down the critical path delay from twice t to t or not. Okay. Now for that let's consider the equation. Now just I am rubbing this. Now just think about. So ultimately I need to think about first this edge. So this is of my interest. Okay. So I am interested to get W new, which is W old plus RV, sorry, RU. Because for this, the destination is U, because the data is flowing from V to U. So that is RU minus RV. What I want to do over here, this is a delay free path. This is a delay free path. If I want to reduce twice t to t, what I need to ensure? I need to ensure that I need to put delay element over here. So that means I am interested in W new. This is W new. So W new I am interested to make it 1. What this W new 1 suggests that I am interested to make it W is equal to D in this particular area. I hope you are following me. This is a delay free path. So I need to break the delay free path. in order to break the delay free path, I need to introduce the W over here. So that I have put it. The W new I want is 1. What was my W old? What is W old?
0.
It was 0. Very good. Because there was no W over here. And that's why I want D over there. Okay. So W old was 0. Now I need to assume RU and RV to satisfy this equation. I need to assume my RU and RV value to satisfy this equation. So I can RV and RU can be any integer. Okay. So maybe I can consider, let's consider RU is equal to 1 and RV equal to 0. Then this equation will be satisfied. RV and RU, which is a retiming vector, it is pure assumption, but that assumption has to be valid. In order to validate that assumption, what I can consider, RU can be 1, RV can be 0. Now one can think RU is equal to 2, RV could be 1. There is no problem. You can choose anything. So here just I have taken RU is equal to 1 and RV is equal to 0. So that means the retime value I am considering RU is 1 now, RV is equal to 0. So this we have fixed above. But there is another edge is also going in. Now since I have fixed this particular node retime value, there will be a implication at this particular edge also. Then I need to find it out. So over there again I will find out W new. Now I am talking about this particular edge, U2V. Okay. So W new is equal to W old plus, here it should be RV minus RU. ठीक है? W old क्या है? 1. What is RV? 0. What is RU? 1. So W new will be. So what this says that if I want to apply a retiming concept and if I want to do retime graph, so in a retime graph I have a U, I have a V, where through this equation I consider that I want D over here. Okay, and then I, with this retime value consideration, I apply this for this particular range, and over that the W new which I got is 0. W has to be integer. That I just said above in my previous slide, because W represent your delay. So delay is nothing but my clock. So always the clock has to be 1 clock, 2 clock, 3 clock. So there is no 1.5 or 1.2 clock. Ultimately, the number of clock has to be integer value. So W has to be the integer value. And with this, I have observed that now my new retime graph is this. Now what is your observation? I have applied a retiming concept through a retiming vector. And what is your observation? What is the critical part for this? Okay, very good. So one of the BTech students has suggested that the critical part has changed. Now the critical part is U2V. But critical path delay is twice T only. This gets changed, but it is still a twice T. That means it doesn't get changed. So this just supports what I claimed initially. In a loop, the number of delay element would remain same. देखो यहां पे मुझे D लाना है, लेकिन D लाने के लिए अगर मैं यहां से D लेता हूं तो यहां से D चला जाएगा. ठीक है, and that is the headache while dealing with the retiming. Now just assume that we will have some liberty. Let's redraw this again. Okay, so let's consider that I have a U, this is U, this is V, and now I having a 2D over here. This is still T, this is still T. Now applied. Now again the critical part, when I start originally, when this is the critical part is from U to V, delay or time, which is a critical path delay, is twice T. My aim is to bring back this twice T to best which I can get it as a T. Now again I am applying a retiming concept, what I did apply previously. So W new is equal to W old plus, I am talking about this age. Always retiming concept start with your critical path because that is of our interest. So I am talking about this age. So that is RU minus RV. What is my intention? My intention is W1 should be 1. Why? Because I want that there has to be one, at least one. See, critical path delay, at least 1D is required to break the path. 2D, 3D, 4D. It doesn't means make any difference for me. Critical path break करने के लिए मुझे कोई भी एक D चाहिए. अभी वो 2D हो, 3D, 4D हो. Ultimately critical path break होता है. ठीक है. So D, W is equal to D. That means I want W new is equal to 1. That's what I want to improve the performance. Now W old was 0 plus RU. Okay. So I consider RU is equal to again 1, RV is equal to 0. So this I applied for U to V. Now apply, this I applied for V to U. Now apply it U to V. So retiming vector are now fixed. So that means W new is equal to W old plus RV minus RU. So W old is 2. What is RV? 0. W new is 1. So now what I can do that if I want to redraw a critical retime graph over here, then the retime graph would be U V. Now with this particular equation I get D over here, and with this I am getting D over here. So now if I consider what happened, the critical path delay is now reduced from twice T to T, because anyhow you observe this part is break, this part is break. So that is the base case, as I said that. हर एक edge पे when you get a delay, that is the base case for you, and that's what you achieve. And now once in the all the edges you are having a delay, then it is up to node. Now the node execution delay, that actually consider as a critical path. So critical path will be the maximum time which is taken by a particular node. So here if I consider both the nodes are taking the same time, That means the critical path delay is T. Now that best I can get for this particular graph is this one. And that's what I have achieved. So that means from twice T, I have reduced it T with this concept. Yes. Here, I means you want to explain again. Okay. So first of all, why I have started from V to U? There are two edges. One is V to U, another is U to V. But I am starting with these edges because this edge includes in my critical path. Always I need to target my critical path. So that's why I have started from V to U. So in a V to U, I applied this equation. Now this equation you need to remember. Okay. So there is no need to actually get, there is a proof also to get this particular equation, but that is not required. Just try to consider that this is the equation. So W nu is equal to W old plus RU minus RV, because this is your destination, this is source. Now when I have started, my intention was clear. I want this W is equal to D because there was no D over here. So that's why I put W nu is equal to 1 because I want this one. Now here you can put 2, 3, anything. So according to that, retime vector gets changed. But ideally, in order to break the critical path, 1D is enough. If you put 2, 3, 4, this W nu value, let's say I am putting 2, then ultimately what it says that I am interested in 2D, but ultimately it will create a problem for you that 2D है, तो 2D यहाँ पे ला दिया, तो आपका critical part shift हो जाएगा. First of all that thing, and second thing is always I need to think about that how efficiently I can get the retiming concept. अगर मैं 2D रख रहा हूँ, तो that means ultimately there is a D is stands for delay element. So I am increasing the delay element. Now in order to have a delay element, of course that delay element requires some area. So I do not want to actually introduce a area burden inside my circuit also. So that's why if in a retiming you need to break the critical path, then always think about a single D rather than thinking about 2D, 3D, 4D. Okay. Only single D is good enough to break the critical path. So that's why I have stick it to D over here. That I want 1 over here. So that's what my intention. Initially it was 0. Now this RU and RV is in my hand. So I will choose RU is equal to 1, RV is equal to 0. You can choose 2 minus, this could be 2, this could be 1, 3, 2. It is up to you. There is no problem. Okay. As far as the difference is 1, you will get the same output over here. Then this RU and RV fixed. So this retime vector I have fixed. So with this retime vector, now I need to see the impact over here, this particular edge. So for this particular edge, U2V is there. So W new is W old plus RV RU. W old क्या था? 2 था. RV क्या है? 0 है. RU क्या है? 1 है. तो मेरा W new क्या है? 1 है. So that's what I am getting. Here you do not have to assume, because here there is no your intention to introduce a D. Your intention was here to introduce it. So that's why I have put 1 over here. And with that, I have fixed my retime vector. So once the retime vector is fixed, then I need to just see the implication on the other edges. So that's what I did. And with that, I observed that this is the retime graph which I got it. Now again, when I say this particular graph, the how many delay element I have in a loop? 2. I applied a retiming. How many delay element I have? 2. So that means number of delay element in a loop remains same. Okay. Now for that also there is a one proof is there. Okay. Just okay. Yes.
Sir, if there is a case where the time of functional block is less than the edge, like edge is 8 and the functional block's maximum is 4, so which would be considered for clock cycle?
See, clock cycle depends upon the delivery part. So that means you are talking about age value is 8. If there is a W is equal to, that means you are talking about 8D over here. Sorry, 8D over here. If there is a D over here, then it is a delay. There is no delay free path. So that means that U and V, whatever the maximum time it is being taken, that is your critical path delay time. And according to that, you need to decide your clock cycle. Okay. Now, as I said that in a retiming, ultimately you need to rearrange the position of D element. जैसे कि मैंने यहाँ पे initially मेरा 2D था, 2D था, तो वो 2D में से D एक रखा और दूसरा D यहाँ पे ला दी. With this I am getting this. Okay. So ultimately in a retiming, when I am talking about the loop, that in a loop, ultimately you need to only change the position of a D element. You cannot introduce the new delay element. Okay. So for a loop, this principle is fundamental principle you need to remember. Pipelining is also there where we will see that over there you will insert a D, but at that time in a pipeline there is no loop. It is single a feed forward network. The data is passing from source to destination. There is no way that from the destination the data is coming back to source. So that is a special case of a retiming where you are allowed to having a new buffer which you can introduce. Okay, so that also we will see. That is in a chapter 3. Okay, so that's why I have started with chapter 4 because pipelining in chapter 3, but that is a special case of retiming whatever we are discussing. Okay, so now let's consider that why or what is the theorem behind which the number of delay element inside the loop remains same. So that we will see. इसको सेव करना SPA2 okay now theorem that number of delay element in a loop before retiming and after retiming is same. Actually, this proof is not there in the book. KK Parhi mein ye proof nahi hai. Okay. Now let's consider a simple graph to understand this concept. So V total number of Vn nodes are there. Total number of, let's say that some finite number of nodes are there, which I am defining V0, V1, V2 like this. Okay, V1, V2, V3 like this. Now it go up to Vn minus 1, Vn and then V0. So this is a loop. I am starting with the V0. I am ending at V0. There is a V. That is a loop is there. Now consider W0, W1, W2. There is W3, Wn minus 1 and Wn. Okay. So if I consider this particular graph And for that, if I want to consider a retime graph, for a retime graph, what would be my equation? Let's say that W0 new. I am interested. So W0 new in my retime graph would be W0 plus R of, I am talking about this, R of V1 minus R of V0. That means for this particular age, I have defined the equation. When W0 new is after applying the retiming value, new weight. Similarly, W1 new. That means I am talking about this. So W1 new is equal to W1 plus R of V2 minus R of V1. W2 new will be W2 plus R of V3 minus R of V2. W3 new will be W3 plus R of V4 minus R of V3. Similar way, Wn minus 1 new will be Wn minus 1 plus R of Vn minus R of, I am talking about this. So R of Vn minus 1. Wnw is equal to Wn plus R of V0 minus R of Vn. Am I right? Now, this is my left hand side. This is my right hand side. Add your left hand side. That means I am considering 1, 2, 3, 4. Let's say that some finite number of equations. This is n. So add all equation n left hand side and right hand side. So that means sigma of W new and sigma. Here if you observe, if I add it, then this gets cancelled. This gets cancelled. This gets cancelled. This R4 will cancel down with this next equation. Similarly, this Vn will be cancelled. This Vn minus 1 minus. So with the previous one, it will get cancelled. So this R0, this R0. So what you are getting? W0 new summation is equal to W0 old summation. So that means what is W? W says that number of delay element. So with this, what you can observe mathematically that the number of delay element when you consider before retiming originally and after applying this retiming equation, I am getting the same number of delay, and that's what the original principle of your retiming. If when you are in a loop, then number of delay element in a loop gets remain same, and with that automatically your functionality will not change. Okay. So that's why in our previous example, when I consider in a loop only D, then the position is just shifted, but critical path delay would remain same. See, for me, if critical path gets changed, then I am not getting any advantage. For me, what is the important is critical path delay should reduce. अगर critical path change हो गए, critical path delay same रहता है, then this is of not of my any use. I have just applied a retiming concept, but with that, nothing is optimized. From where I have started, the same I got it. So ultimately, the critical path delay has to be changed. So with that, in a second example, just we saw that if when I have a introduce the 2D, then probably I have a flexibility that to take out the D and then I can rearrange. Now, there is another method to get the retiming. That is a retiming through cut set. Probably this is not the best time to start with the new method, but whenever we will meet tomorrow, what I will do tomorrow we have a class. So tomorrow we will talk about the second method of the retiming where we want to understand the retiming through cut set retiming. We have already seen the retiming through retiming vector, but now we will see the cut set retiming, which is considered to be a very efficient than the original one. Okay. Okay. So then we will meet tomorrow. Yes. Any doubt, MTech?
Slide.
Uh, now I can read your any questions. Okay. Uh, okay. Sorry. Where it is coming from? Okay, slides you want that I can provide you slide. That is no problem. Okay. So slide I will definitely do it today to all of you. Okay, along with the lectures. So I have also downloaded the lectures and I have already uploaded to the Google Drive. So probably I will do it by today. Okay, I will provide the slides. Okay, thank you. Then see you tomorrow and we will continue with our retiming concept. अभी इसके लिए मुझे क्या होगा एकदम से इंटरनेट को ओके सी यू टुमारो बाय
Thank you, sir.
मुझे अटेंडेंस लेनी है So I'm just opening the Excel so that I can take your attendance. Okay. 1008
Present, sir.
1010 12
Present, sir.
20
Present, sir.
21 22
Present, sir.
31
Present, sir.
39
Present, sir.
48
Present, sir.
70 90 1100 11110 35 1135 50 1150 80 1213 1242 1250 1300 1328 1341 1462 1571